Okay, time for a new video. This one, nothing but applications, no more derivatives for the sake of derivatives. Here we'll be solving problems where we could, if we wanted to, set up an experiment in every problem and verify that our answer is right or wrong. And here's what I mean by that. Before I explain to you the technique, let me explain to you this situation that I want to give you in this first problem. And you'll see how I mean that it's the answer to this problem should be verifiable. All right. So, okay, I didn't write out the entire description of the question, but I thought I'd give you this diagram and explain it along the way. So, suppose that there's this building right here, okay, and somebody is standing on top of the building, and they're trying to lift this plank up to the top of the building. All right, so they have maybe a rope attached here, and maybe there's some machine or pulley that pulls it up, or who knows, but you're pulling this end of the plank up the side of the building. And if you do that, then just cause and effect that this part of it is dragging against the ground, and that's going to have to slide inward, all right? So I'm wondering, if you know how fast that you're pulling this end up, is there a way to figure out how fast this end is sliding inward? That's what we mean by related rates. A rate is something like the top of the plank gets pulled up 0.13 meters per second. All right? That's what a rate is. The rate that the bottom of the plank slides this way is completely related to how fast the top of it slides that way. Okay? All right, so that's the idea. Now, so let's do this. Let's say, to make this question where I have a very firm answer on it, I'll say, how fast will this be sliding inwards when, let's say I'll have to tell you the top is at a certain spot, okay? When the top part is 2 feet off the ground. All right, how fast will that part be sliding inward when the top part of it is 2 feet off the ground? So there's my scenario, and my question is right here. And let's talk about how you'd answer it. Okay, so first thing I would do is try to extract the simplest picture from the situation that you can. And so I'll see that all that we really have here is a triangle. Okay. You know, the plank itself is right there, and that's 5 meters. Okay. And then there's like this side, how far the bottom of the plank is as it slides against the ground is from the building. We can call that X if you want to, or call it whatever you want. And then there's this side, which is how far the top of it is off the ground, and we'll call that Y. And we can make some simple assumptions like the building to the ground is 90 degrees and so on. And then that's the picture. That's what we have. Now, here's how we work this sort of problem. Once we get a picture of everything involved, we start with a true equation about all those numbers. You know, what's the X and the Y have to do with the 5? Well, a true equation would be X squared plus Y squared is 25. Okay, that would be true about this situation. And then here's what we do after that. We take the derivative with respect to time of all the terms in that equation on both sides. All right. Why the derivative with respect to t time? Well, because everything is changing in time. As you hoist this plank up to the top of that building, this distance changes moment to moment. It changes with time. And this distance changes moment to moment. It changes with time. So everything here, both the X and the Y, are functions of time. All right? Okay. So that's what we do, right? That's the first step. And then the first step probably seems a little bit strange, I would imagine. But here's how that plays out. The derivative of x squared is 2x. Okay, that's just the derivative of x squared. That's just what the rules say. But what's the x? The x is something that depends on time. Right, so we say not 2x, but we say 2x times dx dt. All right. Okay, and why is that? Well, I'll give you a rationale for it. It's a lot like, here's a video I made earlier about implicit differentiation. It's a lot like why you say the derivative of y to the 5th power is 5 times y to the 4th times y prime. Why is there the times y prime? Because it's assumed in this scenario that y is some function of x. So here, it's like y times dx dt. Well, because it's not just assumed, but it is in fact the case that x and y are functions of time. So it's like you say 2x times x prime or something like that. I say dx dt just to emphasize that the x is changing in time, and this is its time derivative, the derivative with respect to time. Over here, same thing. What's the derivative of y squared? It's going to be 2y times dy dt. And then on the other side, 25, what the derivative of constants is 0. Okay. Now, all right, what do we do with this now? If I say how fast will the bottom slide inward, if that's what I'm after, I say, well, the bottom's sliding inward at so many meters per second. I have to somehow incorporate the fact that I know how fast the top is sliding up. So if I say that I'm lifting up the top at 0.13 meters per second, then that means that about this part right here, this aspect of that triangle, I know dy dt is 0.13 meters per second. Okay, so I actually know the dy dt is what I'm saying. That as it was told to me how fast this was being pulled up, that's like telling me how fast this vertical height of that triangle is growing, 0.13 meters per second. So, all right, we'll update this then to x dx dt. It turns out that dx dt is what I'm after when I want to know how fast the bottom is sliding inward. Plus 2y times, what was dy dt? 0.13, like so. We'll do a little updating here, 2x dx dt, and this will be 0.26y. 0.26y equals 0. Okay, so I'll solve for dx dt now, and what I get out of that is how fast this bottom part is sliding that way, or how fast this base part of the triangle is changing, all right? So I could do that this way. I could do some subtracting and some dividing, like if I move this over there and I divide by 2x, I'll get 0.26y negative over 2x, okay? All right, now the question that I was asking is answered here, all right? But to get our number, I wanted to know how fast will this top part slide inward when the top, or the bottom part slide inward when the top is 2 feet off the ground, okay? So it's like you're telling me that y is 2, right? That top part is 2 feet off the ground. So let's do this. Negative 0.26 times 2. I know that y is 2. What's the x though? Well, like say if the top is 2 feet off the ground, how big is the base? That's what x is. That's what needs to go right here. Okay? So, well, I could use the Pythagorean theorem to figure that out. I don't know this. I know that the top part right here, the vertical part of the triangle is 2, and the hypotenuse is 5. So I could say x squared plus 4 equals 25. All right, that will tell me how to figure out that base part if the top part is 2. Oh, I put feet. I should have put meters. We got to be consistent with the units. I'm sorry. Meters. So all right, 2 meters. Okay, so this is going to be that x squared is 21, or x is equal to root 21. Okay. All right, so then this number is root 21. All right, let's do our math here and figure out what that number is. Hopefully with a calculator. So let's see, I get 0.26 divided by root 21. And that turns out to be negative 0.057. Okay. With some rounding, negative 0.057. That's what I get. Okay. And units are meters per second. Remember, the distance measurements in this problem were meters. That's why I messed up when I put feet right there. That was no good. All right, so that's the procedure then. It's like that implicit differentiation lesson that we had earlier. Okay. All right, let's look at something else then. So let's try this one. So suppose you had a sphere, like maybe like a balloon or something like that, and it's being inflated, and it's being inflated in a way that the radius is increasing at 2 inches per minute. How fast is the volume increasing? Well, of course, if the balloon is getting bigger, the radius is stretching, then there has to be more space opening up on the inside. So of course, if the radius is increasing, the volume's got to be increasing too. Okay? All right. So let's see, we need an equation first, right? That's what I said. For this problem, like you could draw me the diagram and tell me the worker is hoisting the top of this beam up, or this plank, and it slides up this way and that part slides inward and so on. But I need some equation to work with, right? Oh, I forgot to tell you, why is it negative? There's my final answer. Why negative 0.057 meters per second? Well, the reason for that is that this part right here, that part of the triangle is getting smaller. This part's getting bigger, that part's getting smaller. Whenever any quantity, like the base of the triangle, is getting smaller, its derivative with respect to time is going to be negative, okay? All right. So anyway, so I need an equation. So we have a sphere. What's a true equation for a sphere? The volume of a sphere is 4/3 pi r to the third power. That would be the true equation that relates the radius to the volume. So I have that, and I told you that we would need to take, once we get our operative equation for our situation, whatever it is, in this case I have a sphere, I need to take the derivative with respect to time, because everything here is changing in time. Okay. And I also know this as far as derivatives go. If you tell me the radius of the sphere is increasing at 2 inches per minute, that means that dr dt is 2. And if you want to put the units, you can, but the number is just 2. All right. So let's do this part then. I can figure out how the volume's increasing from this step. So first, what's the derivative of v? It's going to be 1. But v is a function of time, so I have to follow that with dv dt. What's the derivative of 4/3 pi r to the third power? It would be 4/3 pi, okay, that's a constant, so I carry it, times 3r squared, okay, that's the derivative of 4/3 pi r to the third. But then r itself changes from moment to moment, so I have to multiply that by dr dt. Okay, so there's my work from here, and I know dr dt. So let me do a little simplifying and so on. Let's see, with the 3 canceling, I'll get 4 pi r squared, and then dr dt is 2. All right. Okay. So one more thing. dv dt, might as well put the 2 and the 4 and say 8 pi r squared. Okay, so that will tell me how the volume is changing. All right. Okay. Now, let's figure out how exactly is the volume changing when the balloon or the sphere is different sizes. Notice it says how fast is the volume increasing when the radius is 12 inches versus 35 inches. Okay. Now, I would suspect different. If the radius of the sphere was growing at a constant rate, like it is here, then the bigger the balloon gets, the more the volume will be increasing. All right, so think about it. The radius is stretching by a constant 2 inches per minute. The bigger the sphere is, the more volume it's taking on per minute to compensate. So we could do like this. We could say dv dt when r is 12 is going to be 8 pi 12 squared. All right. That's how fast the volume is growing when the radius is 12. All right, so let's see. That's going to be 8 times pi times 144. So that's going to be about 3,600 or so. Here's the number I get. 3619.1 units. Okay, well, volume over time. So that'll be inches to the third power, cubic inches per minute. Okay. All right. So now you'll get an even bigger number when you put 35 in, because the bigger the balloon is, the bigger the sphere is, the more volume it's taking on per minute as the radius grows. Okay. But all right, so it's no big deal. You put 35 in. This is what tells you how fast the volume grows. I'll let you do the 35, but you see, it's not too hard with a calculator to do that part. I just want you to see that you have to have a starting point, and you have to have an equation that's true about the situation. You take the time derivative. You have to incorporate that you know how one of the rates is growing, such as the radius, and then it all comes together about right there. Okay? All right. Let's look at one more. So consider this example where I have a simple diagram, but I'll explain what's happening. So suppose that two planes are flying at the same altitude, and they're going to converge on this point right there, which may be, well, okay, probably we want to avoid that, right? Okay, the planes are flying towards some point in common where they may meet. This plane is 75 miles out from this meeting point, flying at 150 miles an hour. And this plane is 100 miles out from this point, flying at 200 miles an hour. How fast is the distance between the planes changing? All right. Okay, so in other words, like you could say, the planes are going to be so far apart according to that, and then that distance right here is shrinking by so many miles per hour. Okay, so that's what we're after. Now, so I explained this situation. I had a simple diagram, at least to start with. Let me reduce it down a little bit further. Like with this one, I see, as in our first problem, it's just there's a triangle happening, right? There's a plane here, there's a plane here. They're flying towards each other, perhaps meeting at that point. But nonetheless, this point and that point and that point, made by the two planes in the point where they might meet, make a triangle. And I could say, well, this side's going to be X, and this side's going to be Y. This side's going to be R, or something like that. Okay? And I want, I guess you could say, dr dt. I want to know how fast is the distance between the planes changing. That would be this distance. All right, so that's what I'm after. So let's see about getting there. What did I say with the other problems? Let's see, let's start with a true equation. Here's the situation. What equation is true about this distance right here, this distance right here, and those are all the distances and measurements that are involved in this problem. What's an equation that's true about that? It would be that x squared plus y squared is equal to r squared. And then I said, well, what you want to do is, once you get that starting point, take the time derivative of all the terms on both sides. If you do that, you'll get 2x dx dt. Then you get 2y dy dt. Why the dx dt and dy dt? Well, because x and y change in time, because everything's moving. What about over here? R. So 2r dr dt. And this is the thing that you're after right here. You want to figure that out. Do you happen to know these? Do you know how fast this part is changing? Is the plane here flies that way and the base of the triangle shrinks? Or do you know this one? Do you know how fast the vertical, the height of the triangle shrinks as this plane flies that way? Yeah, this plane's flying at 150 miles an hour and this one 200. So we happen to know both of those. Okay. So dx dt is 200. Okay. Well, let me write like this. That's negative 200. Why negative? Well, because, I know the plane's flying through the air at 200 miles an hour, but this part of the triangle is shrinking by 200 miles an hour. Okay, so we need to incorporate the negative. And then what's dy dt? Well, dy dt, this plane's flying that way at 150 miles an hour. The vertical dimension of the triangle is shrinking by 150 miles an hour. So we'll get like that. And then we don't know dr dt. That's what we're trying to figure out. Trying to figure out how fast the distance between the planes is changing. So here's what I'll get out of this. Negative 400x, okay, minus 300y, okay. And then over here, 2r dr dt. Okay, and I think I'm getting pretty close to solving for dr dt. If I just divided by 2r, I would get it. Dr dt is negative 400x minus 300y over 2r. Okay, that's the number that's going to tell you how fast the distance between the planes is changing. Okay, but you need to know where they are. How fast the distance between the planes is changing depends on how far away from each other they are and so on. So the condition of the problem was that this plane was 100 miles out that way and this plane was 75 miles out that way. So I know a little bit of this, okay? I happen to know that x is 100. And I happen to know that y was 75. All right, so I know that. But what's r? For you to tell me that this plane is 75 miles out that way and this one is 100 miles out that way, it doesn't tell you r, but you could figure it out. Okay, see, there's the operative equation for that triangle. If you know x and y, you can find r. So sure, I'm going to get like this. Let's see. So r would be the square root of x squared plus y squared. So that's going to be square root of 100 squared plus 75 squared. Okay. So there, that's the number. That's going to tell me how fast the distance between the planes are changing. So I got to figure all that out. Let's see. I'll pause the video. Okay, so I got negative 500 miles per hour. So that's the distance, how fast the distance between the planes is changing, in other words, okay? All right, so let's see. Let's do with that part being done, let's do this other part. Okay. How much time until the planes reach the same point? All right, now this is a totally separate question than the other one. But say they're flying this way. You know, with the distance they're separated by, and with the speeds they're flying, it might not even be that they reach the same point at the same time. Okay. So how much time until they reach the same point? In other words, what I'm trying to ask there is, will they reach this point at the same time? Because that would be bad, all right? If they're flying at the same altitude towards each other, it's not like this one's going to fly past that one. Maybe it will, maybe it won't. If according to their distances and according to how fast they're moving, will they reach that spot at the same time? So let's do this. Let's figure out if this plane flies at 150 miles per hour and it's got to go 75 miles, how long till it gets there? Okay, so I'll say for plane 1, and let's say we'll call this point A. Okay, plane 1, time to reach point A. How long is it going to take that plane right here to reach point A? Well, distance is rate times time, and it's got 75 miles to go to reach point A, and it flies at 150 miles per hour, so it will take 0.5 hours to get there. Okay, now what I'm wondering is if plane 2, flying at 200 miles an hour, flies for half an hour, will it travel 100 miles and reach that point at the same time as the other one? Well, so think about it. So suppose that this plane's going to be there in half an hour. If this plane flies for 200 miles an hour for half an hour, it will fly 100 miles. It will reach that point at the same time. So we'll say this. Both reach point A and T is equal to 0.5 hours. So if there was an air traffic controller working on some kind of antiquated equipment, then he better divert their paths before a half an hour is up. But yes, they will reach that common point at the same time, and it is in half an hour from the time that they're at these respective positions.